In this video, we'll be going over conjugate acid and base strength. The first intro part will be just going over conjugates and what they are, definitions, and an example of what they are. So we see a couple definitions. So a bronzolaric acid is a proton donator. So I'll just abbreviate that as BL. So bronzolaric acid is a proton. So I'll just write H plus for proton donator. And a Bronsted-Lowry base is a proton acceptor. And we have to really, to do this exercise, we have to pay attention to the forward reaction and then the reverse reaction, and we have to kind of identify what species belongs to what. So we have to look at, like, so when we go left to right, we have to go before and after, and then when we go this way, this is our before, and then this side is going to be the after. So this will be our reactant side and this will be our product side when we look at the conjugate. So so here's how it works. We see that the acetic acid molecule on this side became this. Okay, so this turned into this. So we ask the question, how did it do that? How did it become this? How did it become this from this? And we look at the difference. Here it has the H plus H. Here it has the proton, and here it doesn't. So what must have happened from here to here if we go in the left to right direction? So, well, we see that the acetic acid molecule donated a proton. Who did it donate it to? The acetic acid molecule donated its proton to water. So when we look at this reaction going left to right, we see that the acetic acid molecule is the Bronsted-Lowry acid, because it donated its proton to this. So if we look at it going right to left, going this way, we see that the acetate ion accepted a proton, and who did it accept them from? It got it from the hydronium ion. So when we look at this reaction going from right to left, going this way, then this became the base, and this was the acid, the hydronium ion. So let's fill in those results and write them on the lines here. So the actually we could use a make use of this highlighter. So this and this are conjugate pairs, and then this and this are conjugate pairs. So this was a H plus donator, and it's acting like a Bronsted-Lowry acid. The water is a H plus acceptor because it got the proton from the acetate molecule, the acetic acid molecule. So the water molecule was a Bronsted-Lowry base. Now, when we look in the reverse direction, again going this way, the acetate ion is accepting a proton. So this is H plus acceptor, and the hydronium ion is the proton donator. So this was our Bronsted-Lowry acid when we go right to left, and this was the Bronsted-Lowry base. Okay, so in a similar fashion, we can look at this reaction going left to right, and then again we'll look at it going right to left. So this and this are our acid-base conjugates, and the water also is the second pair. So water and the hydronium are a pair. So this was our H plus donator, which is our Bronson-Lowry acid. This was the acceptor going left to right. So this is our Bronson-Lowry base. And then going right to left, where this is our before and this is our after, this was accepting a proton from the hydronium. So this is our Bronson-Lowry base. And the hydronium ion is our donator. So this is our Bronson-Lowry acid. Okay, so there's a your turn at the very end of this video, and you may want to refer back to your notes to see it. I'm kind of saving all the your turns for the end of the videos just to be consistent, and so that they're not like hidden throughout the video. So you'll find the your turn that's just like this at the very end. Okay, so now that that's squared away, we have like some definitions in place. We could go on and look at what Ka is telling us, and what something called Kb is telling us for the base. So this will have a Ka, and we'll need to look these up and use Appendix D in our textbook. And this is not, we're calling this a base, and it is a base. It doesn't look like a base. So bases, up till now, you may have recognized bases as just as having an OH. So like sodium hydroxide or potassium hydroxide or something like that. Okay, so weak bases are those were all strong bases. This is a weak base. So the conjugate of an acid is actually, the conjugate of a weak acid is actually a weak base. So this will have and it can do equilibrium and all that stuff that goes along with an acid or base being weak. So this will have a corresponding Kb for it. And on the next slide, I'll go over how to convert from Ka to Kb, and we can use the value for Kb to rank how strong or weak of a weak base it actually is, the degree of ionization it will do when it interacts with water. And we can describe that when we find out its Kb, which can be determined by looking up the Ka of its conjugate. So if you look at Appendix D, you're not going to find the Kb for the acetate ion. It doesn't list it. So they're expecting you to know how to convert from Ka to Kb, and then also understand everything on this slide, that this is actually a base. So, okay, so let's go ahead and describe how to do that. So let's go to the next slide. Okay, so using Ka to tell acid strength and conjugate base strength. So here's a example of strong acids. You'll notice that strong acids just do one arrow, and I just want to caution you again. This is from our previous video where I was saying you need to know the strong acids. I would actually recommend that you just kind of pause the video, or even stop the video now and turn it off, and come back when you've memorized the 7 strong acids. So I wasn't kidding in the last video when I was saying how important it is to know those. It's such a basic request, but it's always surprising to me that it's just taken for granted, because stuff like this gets really tricky, especially if you don't know the strong acids immediately. So the reason you want to know them is so that you, first of all, that you know all the weak. So if it's not strong, it's going to be weak. But this slide right here is made so much easier if you know the seven strong acids, because the conjugate of a strong acid is not a weak base. Why not? Because it doesn't go backwards. See that arrow? It does not go the other way. So, how do you know which ones don't go the other way? You have to memorize them. I don't like memorizing. I don't like memorizing anything, but this is one of those things where it's pretty simple because there's only seven of them, and it makes this kind of stuff way easier. So, I'll just go, I'll put this now. I'll put this bullet point now that anions of strong acids are these. So I'll go ahead and list them here. So I like to list all the halogen ones first. So Cl minus, and this is going right down the group 7, column 7. So the chloride ion, the bromide ion, the iodide ion. So that's 3. We got 7 total. So we got 4 more. Now the polyatomic. So nitric acid is HNO3. So it's anion, nitrate ion. Um, the chlorate ion, which makes chloric acid, and the perchlorate ion, which makes perchloric acid. Um, these, you'll notice I left one out, sulfuric acid. This one has like kind of like its special, it's a special case, because the conjugate actually is weak, the first conjugate. And then the second conjugate is also weak. So this has like this one is kind of like a special case because it's polyprotic. So I'm not going to list that one here. But these 6 right here, these have no basic properties. So they don't do anything. If you just had a beaker with this or the nitrate, the chlorate ion, the pH would be 7. It's going to be neutral because they don't do anything with water. As you see here, they don't go backwards. Okay, so they don't do anything with water, hydronium. They don't do anything. So um so these, they don't do anything or interact with anything or anyone. Okay, so they're not basic at all. And how do you know which ones these are? You have to have them memorized. Okay, these. Here's another kind of like curious case with water. So water, H2O, you kind of noticed it on the previous slide. It can act like an acid or a base. So we say that water is, this is a vocabulary term. We say that water is amphiprotic. Amphiprotic. And that means kind of like if someone's like ambidextrous, then they can write with both hands. Okay, or they can throw with both hands. So this is, so water is amphiprotic, meaning it's an acid or a base. So and H2O, by comparison to other weak acids and weak bases, is a very weak acid or base. Okay, it's actually the Ka. I've seen it. I've looked it up a few times in the past, and the Ka is something like May need to review my notes on this, but it's something like 1.8 times 10 to the negative 16th. Um, you'll see that by comparison to other weak bases or weak acids, that it's going to be really, really weak. So for other bases, we're going to use the Ka to tell. And you'll see that when the Ka increases, we know that means if you have a high Ka, that means the equilibrium. If you have like here's a generic acid and it dissociates into its ions. So when Ka is big, that means that tells you that a lot of stuff goes over to the right, and the equilibrium lies heavily on the right side. Okay, or relative to other smaller Kas, then it's going to make more ions. So we say that when Ka is big, that means it's a stronger. I'll put it in quotation marks, stronger, because it's still considered weak, but it's a stronger weak acid. The corresponding base, however, if you have a high Ka, is going to be low. And there's a conversion, and we'll go more into this conversion and how it's derived. We'll probably do that in class, but this will actually kind of like get you through this video. So the KB conversion goes like this. So there's water has a equilibrium constant called Kw. So Kw is the equilibrium constant for water. And it has a value of 1 times 10 to the negative 14th. And this is by definition, so it actually has infinite sig figs, so it's because it's defined to be exactly 1. So for the KB conversion, it's based on Kw. So Kw equals Ka times Kb. So actually, I'll be having a video that goes all into this. The whole video is on this, what Kw is, and we'll go over how it's determined. But for now, I just wanted to show you how Kb is converted from Ka. So Kw, we set it equal to Ka. So this is 1 times 10 to the negative 14th equals Ka times Kb. So if we solve for Kb, then we get Kw, which is 1 times 10 to the negative 14th over Ka. So I'm going to box this in a red color because it's really, really useful to know, to use when we get to the exercises at the end. Okay, so so here's a question that we're going to try to answer. Which is a stronger acid? So we have the hypochlorous acid, and this comes from the hypochlorite ion. So this is hypochlorous acid versus hydrocyanic acid. So which is a stronger acid? Well, we have to go look at our appendix D, and we find that the Ka for hypochlorous acid is 3.5 times 10 to the negative 8th. And the Ka for hydrocyanic acid is 6.2 times 10 to the negative 10th. So it's pretty easy to tell that this is greater than this. So that means this side will make a little bit more ions than hydrocyanic acid. So the stronger acid then is going to be hypochlorous acid. So this one is stronger. Okay, so now for a more involved question is which conjugate is a stronger base? So which conjugate is a stronger base? So we're going to look at this versus this, and when they interact with water. So not the hydronium ion. We're gonna actually interact it with water. So this would be like actually these are actually called salts. If you have like NaOCl, or if you have sodium hypochlorite. So this would immediately dissolve, so it's known to be fully soluble. This is a spectator, and then this will actually go on to interact with water, and then it will do this reaction here. So, um, so if we convert the Kb, we could do this. Okay, we could go. Okay, since this is the stronger acid, therefore its conjugate is going to be weaker than this one. So our final conclusion is that that Cn minus is going to be a stronger base than this one. This is the correct conclusion, but I wanted to make it more concrete by converting their Kas to Kbs and then comparing just the concrete number just to make it super crystal clear. So we're gonna use the previous equation and the equilibrium constant for water and convert. So this is 3.5 times 10 to the negative 8th. So you could actually, if you're dividing exponents, you could actually you may or may not need your calculator, but to for a quick estimation, this is actually a multiple choice skill. We'll be going over all this stuff and skills on that are AP exam specific and how to estimate exponents. But if you take negative 14, so if you divide exponents, this would be like negative 14. It's like subtracting the exponent, so you'll be minusing a negative 8, which gives you negative 6. So your answer is going to be somewhere around 10 to the negative 6. But if we plug it in our calculator, we'll actually get 2.9 times 10 to the negative 7th. And we'll do the same thing for the cyanide ion. So 1 times 10 to the negative 14th divided by 6.2 times 10 to the negative 10th. So we should get, just if you wanted to estimate, we should get something around 10 to the negative fourth. If you want the exact value, I have 1.6 times 10 to the negative fifth. So here we see that this equilibrium this will actually accept a proton a little bit better than this one. So this is going to be, so the cyanide ion is going to be a better proton acceptor than the hypochlorite ion. And we could see that. So we came to that conclusion just by looking at the Kas, and we say, oh, since this is a better acid, its conjugate's going to be weaker. So that's perfectly okay. But just to drive the point home, we can find the Kb and then look at the Kbs and say that, okay, this one is to the negative fifth, so it's going to favor this side more than this one will. So this one will go to the right more than this one will go to the right. So so conceptually, we came to the same conclusion without using our calculator, just by looking at the Kas. So we say that this is a stronger base than the hypochlorite ion. All right. So okay. So here's a table. This is from the old textbook that we used to use. But I kind of like the table that they have here because they organize them. Your appendix organizes them alphabetically, so it's kind of nice that you could find them by alphabet. But I do kind of like this one because um, it lists them in order of Ka, and you see the arrow right here. It clearly labels this is increasing in acid strength going from up here. So these equilibriums are going to lie more on the ion side. And then these, I mean, they all actually favor the molecule side, but relative to each other, these are heavily on the reactant molecule side, these over here. So these are exceptionally weak. Okay, but they're still acidic. It's going to make the pH a little less than 7, but they are strongly favoring the molecule side. So the higher the Ka, the stronger the weak acid. Okay, so I'm gonna do this exercise, and you'll see at the very end there's another your turn that is very similar to this one. So this says which is a stronger base, and we're our appendix or any table in the acid base chapter 14, um, will will not have the KB, so we just have to go off of the Ka that they give us. So for this one, we have Cl minus versus H2O. So this must be recognized as a anion. This is an anion of a strong acid. I'm gonna write Sa for strong acid. So this is not basic at all. Okay, so H2O, which is super, super weak, but it's going to be better than this one at being a base. Okay, so now we have this, the nitrite ion is going to be a better base than H2O because H2O, if you go back a couple slides, is going to be way, way weaker than this one. So this is a stronger base than this one. We don't really need to look if you're ever comparing water with an actual weak base. So if we write out the acid, we know that that's a weak acid. So its conjugate is going to be a weak base. So this is the weak acid, and this is its weak. This is its weak base. So this is actually a conjugate of a weak acid, which is a weak base. So this one we have a weak base and another weak base. So we actually need to look these up. And if you do look this up, this is, I believe this is, I'm going to have to find this. I had to look it up on a table, and it's a phenol. So phenol is you will not find this in the appendix, like I was saying. What you're gonna find is this. You're gonna find C6H5OH. Okay, which is actually it's actually benzene. So it's a that 6 means a six-membered ring. And the name phenol comes that prefix phen is like the phenyl ring, so you'll have a benzene ring, and then instead of an H right here, it'll have an OH right here. So if you write out the condensed formula, then this is what you'll get. So this is the weak acid, and this is its conjugate base, which is a weak base. And then this one has to be recognized as, so if you pretend there's an H on the front, this is a weak, so this is hydrocyanic acid. It's a weak acid, and this is its weak base. So if we look up the Ka for this, then we get for hydrocyanic acid we get 4.9 times 10 to the negative 10th, and for phenol we get 1.3. So for phenol we get 1.3 times 10 to the negative, where did it go? I lost it. To the negative 10th. Okay, so this is greater than this, which means this is a better acid than this. So this one's conjugate base is going to be stronger than this one because the other one's conjugate acid was stronger than phenol. Okay, and you could convert this and calculate KBs if you want. I'm not going to do that here. I'm just going to kind of go by the KAs and then reverse it in my head. So now we'll go on to the last one. So we have this and this. So which one's a stronger base? Well, this is kind of a test. So I want you could pull up your appendix D and you're not going to find this. You know why? It's HNO3 is a strong acid. So this is not a base. And same thing with this one. This is a strong acid, perchloric acid, and this is its conjugate, which is nothing. It's not a base. So watch out for those. I put a few of those on the your turn, and just so you could kind of like look at Appendix D, you know, realize it's not there, and then finally, because you haven't memorized the strong acids yet, you'll kind of do it like the painful way and of like wasting time and looking it up on the appendix, and then you'll realize finally it's not on there because it's not a base. So here's the your turns. This one is kind of like this one's kind of like the first one. I left these blank here. I left these blank so that you have to fill these in, fill in these missing parts of the chemical equations. And then kind of like the first slide in the video, you have to write in the whether it's a acceptor. So you want to write it's an acceptor or donator here and here on these lines. And then whether it's a bronzylate acid or base on these lines. Okay, so again, you have to go from left to right, and then you have to look at these and go left and right to left, and then see what happened from this to making this. Okay, so I'm going to go on to the next slide. So here's the other your turn. So this is asking which is the stronger base, and it's just like the one that I just did. So you're going to have to use Appendix D to look up the KAs on this one. Okay, that's the end of our video. See what you guys come up with on these your turns.